those great introductions. So, I hopefully the audience knows you're all immensely qualified to talk about, the early history of the CubeSats. You touched on it a bit, but I want to hear from the other panelists. Now we take for granted an elementary school can build and get a CubeSat launched by NASA. Perhaps starting with Professor Twiggs, would you like to talk about some of the early reactions when you talked about we're going to build a satellite this small and get it launched that, weren't so positive?
Yeah, we got lots of interesting comments, as I'm sure Jordi did. The aerospace industry and particularly kind of the amateur satellite community was very critical of us. I remember some of their comments was, of course, that it's too small to do anything useful. Besides that, you university people are not smart enough to build a satellite. Well, you know what happens when somebody tells you that you can't do something. Um, you recruit a bunch of really smart students and take credit for what they do. But it's an interesting thing that, to me, it is such a fantastic thing to put something in space and study space and we keep seeing that there is still a big spark out there for young people that are interested in space. It just, from when we first started, a few big projects had started, the constellations and for communication, and effectively they went broke. And nobody would put any money into it. But right now it seems like the venture capital people are chasing people around, trying to get them to spend their money. Maybe not always the best way, but there's some real successes. You look at GOM Space. And a number of them are doing absolutely great things that you would never thought they would do. But again, back to the back to the education standpoint, one of the things that we in the university program suffered was when it became popular, especially from the commercial side, is we lost low cost launches. Our original launch was like $30,000, and then boy, it jumped up to 120. Well, it's pretty hard for a university to raise $120,000 for one CubeSat. But fortunately, NASA eventually jumped in with what they called it the Alana program then, and Big Daddy, the guy that run that, really brought it along a lot of ways, and was able to get the universities involved. We have a program I'm working with Nick Pugh down at the University of Louisiana. Nick has actually launched 3 CubeSats, have an Alana launch for the 4th one, and I kept talking to him about I wanted to build something that was really inexpensive, and we had a program earlier called ThinSat that we launched on the 2nd stage of the Atari's rocket. And the way you can reduce the cost of launches is you got a given volume, make more than one satellite in that volume. So we're back on a program that's like the ThinSat. We just call it SlimSat, which is another name, that we can take a 3U and launch 20 or so of these little SlimSats out of it. And we want the SlimSats to be very simple. If you build the satellite for the first time and you get simple data back for it, maybe you got a magnetometer, maybe you got light sensors, you're looking at what the battery is, you're looking at these things. that's new to you. You don't have to get data from the universe in order to be new to a student. So we're looking at building a small satellite. Nick has got a design that he's used a lot on balloons that we think we can put together with a LoRa radio in, which is not going to give you much data, but that's okay. Get some data back, but go through that cycle. And we hope to do that. We put in a proposal to NASA. I guess they call it the CSLI program now, which is the Alana program. We put in a proposal for that, and we thought, well, after 3 or 4 years, proposal will get accepted. They accepted this the first time, and we were, we got to do it now. So we have an CSLI launch program, and NASA seems to be favorable of what we're trying to do. So at the rate we're going, we want to pick up students that are freshmen or no more than sophomores in high school and have them launch their SlimSat before they graduate from high school. And I think if we can do that, and I know we can do it, there is no question about it, we can do it. That imagine what they're going to do when they get in the university. They have been through that. But one of the things that we kind of shield them from is the difficulties in doing this. It's the difficulties in getting a launch. It's the difficulties in meeting all of the requirements, the FCC requirements and all of that. But the new CLSI program is really helping out on that because NASA gives them a budget of $300,000 to run that particular launch. So they will get consultants. They will get, get the things that you need to make sure you have a successful project with their budget. We don't get any of it. But that's okay. That puts the challenge on us. So I hope that we can prove this SlimSat project. And what we want to do is launch off of the station, but not release anything till we get down. So we've only got about 6 months of orbit life before we deorbit. And if we could get 1 or 2 of these launches a year, think of the opportunities that the students will have. I'm really excited about it because as Aaron and I have done, go back and interview a lot of the students that were in the CubeSat program, it is the highlight of their life. And we often hear senior engineers saying, why didn't we have something like this when we went to school? And so it's something that's good. It changes students. It gives them confidence and it gives them something that really makes their education different and very, very useful. So thank you, Jordi, for doing all of the hard work that you did in getting this program going. All I did in this program, I get credit for a co-founder in it, but all I did was buy that little plastic cube and work on a prototype for the P-pod. And then I sent him to this guy that I knew. He and his students do things. They make things. And he did. So really, I'm the little guy that I kind of picture myself as the guy that has this battery on his back with a couple of jumper wires. And I go around and I try and get projects started. I don't know how they're going to get done, but if I can get people enthused enough about it, they get going on it.
Thank you, Bob. And I have to jump in because the thing about the enthusing is a critical part. And that's and I go back to the idea that we had, 20 universities from the beginning. There were 20 universities building CubeSats all around the world. And that was Bob going around the world and telling people we're doing this. My students still tell stories about the days that I would go walk in the lab and say, we need to get this PPAD thing figured out because Bob has already sold another 3 satellites, or 5 satellites or 15 satellites. And we got calls from universities saying, "Where is the standard?" Because we need to start building, and that was really interesting to see how Bob could energize people. But that's the other thing that I think both of us committed to the standard, and that was we didn't have anything like that before. Nobody could start building and say, "I'm going to put this thing together, and I know it's going to be able to fly because there is all these rockets that have standardized accommodations," and that didn't exist. Everybody was just, everything was custom. The analysis took forever. Couple loads on all the satellites, on all the rockets, and that was really, only universities could have done that. If industry had tried to do something like this, they would have been competing with each other and keeping things proprietary, and it would have never happened. So that's I think one of the ways in which, when industry said, "No, you cannot do that, it's not going to work," is because they were looking at it in their own way. And I got, at the beginning, we got a lot of people that said, "Why don't you make a bigger one? Make it 12 centimeters instead of 10 centimeters. I need a 15 centimeter one, and I have money." But we were like, "You may have money, but I don't have the horsepower to requalify a Peapod that's bigger," because we didn't have any funding, and the students were pegged, just doing their best, qualifying one system. And that actually worked to our advantage. If we had infinite funding and infinite time, NASA way, we would have launched the 3Us once, and the next launch would have been bigger satellites with a bigger box, a different design, and everything would have been changing all the time. And the fact that there was no funding forced us to be frugal and to reuse the things that we had already built. And I think that made a humongous difference. And it also allowed Bob to go around selling more of these things, so that I had to worry about putting them up.
Before, I believe we
Aaron.
want to take a picture
Yes,
before.
Aaron, we need to break for the group photo session.
And then we'll let Professor Schilling right after the photo session.
Yasuda-san, can you take the picture?
Yes, please turn on the camera and prepare for making a smile. Okay. Everyone, are you ready?
Yeah.
Okay. 3, 2, 1, cheese. Okay, please show me your teeth like this. Okay. 3, 2, 1, cheese. Okay, we have lots of participants today. Okay, one more. Okay. 3, 2, 1, cheese. Okay, thank you very much.
All right, should we just go right back into it?
Yeah.
Ray, do we go right
Yes.
back to panel discussion?
Yep.
Yes, please.
All right.
Go ahead, Aaron.
Professor Schilling, I think it's your turn.
Okay, thank you. No, I think standardization was a key. So not everybody had to reinvent the wheel. So different partners could combine their equipment. Yeah, one produces telecom, the other one produces the board computer, the batteries, and so on. And this combination was quite helpful. So it raised international cooperation a lot. And what we also saw in the early days, other agencies jumped in, like NSF promoted payloads for CubeSats. Yeah, so new measurements instruments came up. There were programs initiated in other countries, not only in the US, but also in Europe, in Japan, everywhere. And this contributed a lot to the success. And also a lot of student exchanges. In our team, we had Japanese students, we had Romanian students, and it was a team composed of 10 different nationalities. Before, this was not possible. But thanks to the standardization, it became reality.
Professor Tsuda, I wanted to ask, did you have anything to add to that? But I also was wondering,
Yes.
because you mentioned it in your introduction, that a big part of the process of developing your CubeSat was the minimization of the complexity of the CubeSat, and talk about maybe how that helped as well. But yeah.
Yeah. So in the very early era of CubeSat, the CubeSat activity is attractive because everything was new, and because we were ignorant, so we did not know how to make the satellite. So before we know about how to make the CubeSat, we didn't know how to make the real satellite. So that's um, more challenging. But because of that, so we had a lot of freedom, and we can challenge. So even though the uh, the satellite professionals already knows how to fabricate the satellites, real satellites, we sometimes challenge the something that was already done, but in a new way, or in our own way. But in that way, we could make our own world, and then we can feed back to the satellite, the real industry. And that kind of feedback and the cyclic process was one of the very big contribution to of the CubeSat activity. But I am now in academia, still in academia, and what my concern, I always think I also think that the we want something innovative, and because the CubeSat was so popular, become so popular, so it's not, for me, it's not new enough. So what will be the new things? So standardization is a very good thing, very good to broaden the activity to worldwide, but in uh, in at the same time, uh, we don't stop our activity, and we should make we need to make something new based on the current standard, to expand to like more smaller satellite, or for like Jordi and Twiggs says, to younger generation, or like I am now doing, to further deeper space, and so on and so on. So the CubeSat is already very, very popular, but I think that's just uh, the initial step to the next world, next step.
So I think that's actually a good transition to another question which I had, which is, what advice do you have for those listening, uh, both to, how should they approach their CubeSat program, and then maybe how should they use their CubeSat experience to continue working in space?
I'll say one thing, and let everybody else jump in. I think you said a word that's very, very important. You said a CubeSat program. And one of the things that we saw, because we were launching so many, we saw a lot of different universities doing different things. And if you start a CubeSat project that is a satellite, you will launch one satellite and stop. But if you have a program where you say, I'm going to use CubeSat to learn about whatever my university or my nation or my group is interested in, and on the first one we'll do this, and on the second one we'll do this, and the third one we'll do this. Those are very successful and resilient programs where even if the first one fails, you're already working on the second one, and nobody can really stop you. But if you have a single project, that's a lot more fragile, because we had some universities that they had a ton of support from the dean and the president of the university. Everybody was excited. They launched the satellite. And then when they asked for money for the second one, it was like, well, we already did it. It's not exciting anymore. So we're going to go fund something else. So I think that the grain of salt or sand that I would want to put on our pile is don't think about a satellite, think about a program, which is exactly what you said, Aaron. And I don't want that to get lost. I know. And keep it simple.
I fully
like
agree. Program is important. But here's a question usually arises. How do we form the transition between different student generations?
Yes.
Yeah. How can we keep experience? So this would be an essential part of the program to answer these questions. And usually you can use PhD students who supervise younger students and guide them, and this way to have an evolution of the program. But it needs organizational efforts.
Yeah, one of the things in the STEM education that I see is you'll have people that'll provide something for students for a particular mission, and the students will do that mission, and then, like you say, nothing else is done with those students after that. It's kind of a one-shot thing, and I think in the STEM education program, what we need to do is focus on providing something for the students to do a mission. But like you say, it needs to follow on with that. One of the things that we were involved here is to provide a device to use during the eclipse that we had. We had the eclipse run right through our place in Texas, and we made a device that could record, temperature, pressure, humidity, and store that, so you could record what happened during the eclipse. But when the eclipse was over and they got the data and looked at it, it was great. They're not doing anything more with those devices.
Mm-hmm.
But one of the things that maybe I'll challenge you to think about to get students started is, what if you can give them something that they wear like a badge that measures the environment? We see so many times that the environment at the school, the air quality, other kinds of pollutants around. But if they wear this badge all the time, they can pick that up, they can monitor it, and put it in a national database, and hopefully have some influence on what is done in the environment around their schools. There's so many schools that are next to a freeway. What the environment in that school is like. And I'm trying to think of fun things that students could build, or you could help them build as a project, but they have a continual use for it. So think about that as a starter. When we start students in a program, even at the university level, the first thing we teach them is how to solder. And we have this little thing called a jiggy, that all it is a little PC board that has a motor, it has a light on it, and a battery on it. And what you do is you put little wire legs on it, and you turn it on, and it runs around. Okay, they've got something that moves there. What's the next thing? Hey, do something that they can fly on a balloon and progress. That's the way you progress up. You can't lay a satellite design in front of them at the very beginning and say, okay, build the satellite. So it's the progressive program that you need, but we need things that that go into the school for the kids that have continual use, like monitor the environment, so on.
One other thing that I would say, if somebody's starting, is that there is a huge community and a huge legacy of CubeSat missions and know-how. And I think sometimes people feel like they have to do everything themselves, it's like I have to go and study and I won't ask the professor for help. I think that that's a mistake that sometimes people will do. And there's a wealth of resources out there that you can call. And most people in the CubeSat community will help you. If you have a problem, if you have a question, they'll jump in and answer and try to make you succeed, because that's how the whole thing started. And everybody benefited at the beginning. Even that you will go to companies and their memory of, like Bob said, their memory of the CubeSat is very, very positive. And if somebody goes to those guys and says, "Hey, I'm starting a program, can you do something, or can you tell me something, some advice on how to start?" They will totally do that. So that's another thing that's very important, to take advantage of the people who've been there before.
Actually, so that's, just to somebody mentioned that on the chat. Professor Schilling, do you have it?
No, I think usually agencies are very willing to support, to provide some budget for program development. So in our facilities, we had support from the European Union, we had support from national government, and could this way set up related programs. Yeah, and they always were very keen to include hands-on exercises. Usually, space programs are theoretical before the time of CubeSats. But now we can have hands-on, and as Jordi pointed out, that's something also industry appreciates a lot. So we can integrate support from all kinds of sources to develop programs. We just need to look around. And I think international cooperation, that's a cornerstone of the CubeSat programs, usually. Yeah, so you should not be afraid to approach others.
I agree. I believe just reaching out to those who have flown CubeSats already, even if you're from a country that has never flown a CubeSat, you could reach out to just another CubeSat program and they can provide excellent mentorship.
I think also the space education programs nowadays are mainly international. So if you get scholarships to go abroad, you will find international student programs, including CubeSats.
Professor Tsuda, did you have any kind of things to add, or we move on to the next question?
Let's see. Okay. So in addition to Dr. Schilling's talk, the opinion, I think that I am now in JAXA, and the like a national agency is willing to support this kind of the activity, CubeSat activity, but it's not to. We are not trying to make the our own CubeSat by the national agency, because it's too small or too incapable from the viewpoint of from the national agency. But we know that it's a very effective for the education or for technical skill development. And so I think that there's a lot of room between the current CubeSat state-of-the-art CubeSat level and the real the more bigger satellite. I think there are a lot of useful way of using the CubeSat in the real space missions, but still there are a lot of missions that cannot be done with the CubeSats. Bigger satellites can only do that kind of mission. So in between that, there are a lot of real serious technical hurdle that we can feel. And so in that portion, I think there's a room for investment in terms of technical educational opportunity or international collaboration opportunity, and so on.
Excellent. Another question I think that I would like to ask you, I think you could provide, given this group, you started out as a student in the CubeSat world, is what do you think programs can do to further entice students to come and join and stay motivated to work hard and see these missions through to the end?
Okay, so from my point of view, yeah. So when I was a student, I was really fascinated by the concept of concept and CubeSat because no one had done yet, and innovative things, new things are always attractive to younger generation. That's a very huge motivation. So what is the attractive things for current young generations? So that's the question we have to raise. And the one of the very simple and the answer would be to go to somewhere we have not been, like deep space. So that's like a Mars or to asteroids or to Jupiter or somewhere. And yeah, 10 years ago or 20 years ago, we did not have CubeSats. But now we have lots of CubeSats all over the world. But now we have just a few numbers of deep space missions with the very small satellites, like a CubeSat class satellites, spacecraft. But 10 years later, we do not know. And probably many young people will be attracted by that. Just one idea.
No, that's a great idea. Anyone else like to talk?
Yeah, I think CubeSats have a limited power budget usually, but for deep space we need bigger ones. Yeah, but CubeSats play a role as companions. Yeah, we can have baseline distances for observations, things like this. So CubeSats are a great tool to complement the big satellites. So I would not play a conflict between small and big satellites, but we should take the best of both worlds in order to have best performance at the end. And CubeSats are a great tool for distributed systems. Yeah, so we can complement big ones, but we can also do distributed measurement systems, sensor networks in orbit. When I was young, I was grown up in the big world in computer science with IBM mainframe computers. Today, we have the same performance in our pocket with the smartphones, and it's a distributed network system. And I'm sure also in space, we will encounter something like this, to have small devices, but distributed and cooperating. So new measurements principles will become possible this way. And I think also in education, we must focus now possibly on constellations, multi-satellite systems. Yeah, this might be one of the next steps we will encounter in space, cooperating spacecraft, small ones as well as small and big ones composed.
Well, one thing I think this is very, very interesting, that the collaboration and the big small satellite, like Hera, has a big spacecraft and a small spacecraft. But I think one of the things that we learned from CubeSat that was very interesting is we didn't know this, but a lot of the rockets had a lot of margin. There was a lot of pounds of launch capacity that were being wasted every year. And we used those to learn by doing things that were small satellites. And I think we may end up finding the same thing. There is a lot of missions that go interplanetary that carry a tremendous amount of margin. And when they launch, you could put more things in them. But we don't have the accommodations. And people always talk about the Mars landers have this tungsten ballast for the aerodynamic stability of the system that they drop. And it's just hundreds of kilos of metal that they're flying all the way to Mars and they don't do anything with. So that's another place where I see some interesting opportunities, is that the idea of making useful ballast. I mean, the first CubeSat launch in the US, the orbital science team called it partially useful ballast, and they put us in a place where usually there's a big plate of lead that is used to balance the rocket once they know what the margins are. And then what they said is, they said, well, we can take some lead out and put up 3 CubeSats. And I think we may see the same thing happening in interplanetary. And I think that's one of the things where I think you're correct, that the big satellites do more things, but we cannot take risk. And I think that's the other part that we haven't talked about, is that CubeSats allowed people to take risk and say, I have this idea for a new sensor, but I don't know if it's going to work. In theory, it should work. And they would put it up and it worked. Everybody thought that the XI4 electronics commercial off the shelf, they're not going to last more than a month, but we put it up because we could try and take the risk, and it's still working. So it proved everybody wrong. So I think that's a thing where we need to expand that risk-taking and creativity beyond LEO. And I think CubeSat or something similar is a good way to do that.
One note I wanted to kind of add to this, as something my background is in interplanetary CubeSat, so I feel like I could add, is you could also take simplicity beyond Earth orbit, taking very simple single measurements using smaller instruments like they do in Earth orbit, and taking those measurements in a brand new place could be a way to get around concerns about needing too much power, needing too much volume, and instead keeping the scope and ambitions of these interplanetary CubeSats very small and narrow.
Well, and that's the thing, that interplanetary, you got me going, because it's my latest beef, is that we need to start doing. There is these big calls, like NASA has discovery opportunities, and somebody proposes going to Venus, and somebody says let's go to Titan, and somebody says let's go to Europe, and they pick one. But that means that nobody's going to the other places. So they propose a mission that gets a ton of data, and if it doesn't get selected, they got no data. So what you're saying makes perfect sense. Send something to get a little bit of data. It's infinitely more than zero. So
Professor Twiggs, what about you? Do you have any, you have a lot of experience about how do you get people engaged in new CubeSat missions?
Well, one of the things I was just thinking about, NASA has this program through NanoRacks that's managing the lockers on the International Space Station, and they have things called nano nodes, which are essentially boxes that are the size of a 1U, a 1.5, 2U, I think maybe even a 3U CubeSat. You put your experiment in that and hook it up, and they give you the power and they give you communication. So what you do is have your experiment in there and get your data back and send commands on the internet. That saves so many problems compared to having a free-flying CubeSat. That opportunity, like you say, would really be good payloads on big spacecraft. What if there was a rack on the geostationary satellites that would hold a bunch of experiments and again be able to use their power and their communication? One of the things that, when we initially started out, we were just concerned that we could get the spacecraft to talk to us. We weren't too interested in payloads initially, but once we knew we could communicate with a satellite, then we started thinking about payloads. And from my standpoint, I'm not interested in the satellite anymore. I'm just interested in the payload. I want to get data back. And are there opportunities like that, like I say, on some of these planetary missions to just fly your payload? I think there ought to be a challenge. Here's a box that you can put something this size in, and we'll give you power and communication. And I think they'd find an awful lot of things that do that. And talk about an opportunity for a student for the second or third project beyond on the CubeSat. It's this thing that's mentioned. It ought to be a program, not a particular mission. And so we ought to look for other places to put these payloads. To me, that's the fun thing, is to build a payload that does something that's unique to your interests. And so I think what Jordi said and what we're hearing from Professor Tsuda and even Klaus is there's opportunities there, just like there was lead on the launchers. Get rid of the lead and let's put some student experiments on them.
And I think one thing that it's really great that you bring in nanoracks, because that's one of the things about standards, that they kind of break molds and you start doing things that you didn't expect. And now you have something that's inside the space station that has nothing to do with deploying into space, but it uses the same size and the same form factor. And you can make instruments that are standardized, and you can put it in a CubeSat, or you can put it in a spacecraft, or you can put it inside the station. And I want to show you an example. Do you guys all know what this is? That's a charger for your car. And I remember the first time I told my kids that was for the lighter, to light up your cigarettes. That's why that was on every car. It wasn't there to charge your phone or plug in your computer or have an inverter, but it was a standard that was in all the cars. And once you have something like that it's standardized and it's in all the cars, interesting things happen. And that's what happened with CubeSats. You had this standard that was in all the rockets and you could launch it. And now all of a sudden you make 12Us and 6Us, and nanoracks makes things for the space station. So I think that's the way to think about it, that once you standardize, expand and do other things with it, you don't need to mess with the standard, but you can use it in very different ways. I think that would be fun to see.
One of the programs that we're involved with is putting things on the NASA zero-G airplane. And we've built a thing where you have a processor and a camera, and then you have about a 2-inch plastic box that's filled with something, and the students put things in that box and then try to try to take pictures of it while they're on the loop on the NASA zero-G airplane. And then what we're also looking for is, now can we take this same concept and put those things in the nano, the nano tube that, or the nano racks that has on the station? Can you extend what you're doing on the zero-G airplane to the space station? And that, and then if you want something that's completely independent, then you can do a free flyer. But there is so much more complication and requirements to get out on a free flyer that maybe we can get the students to start with just a payload that we get on the station. And the nice thing about that is they bring it back. You get it back rather than as your satellite and you lose it. So maybe that's something to think about, is what other things does NASA have, resources that we could use? I know they fly balloons, they fly rockets and other things, and maybe that's a first step for a lot of the students.
I believe now it's well, it might be a bit early, but maybe we could start taking questions from the audience.
Aaron, or you could select some from the chat.
Well, here's a good one we could talk about, is where do you find international CubeSat programs? We could start with UNISEC, is of course a great organization. Maybe anyone else have some examples they would like to share?
I think UNISEC is the best example. Ray, just contact Ray. Chill. Actually, Ray, do you want her to jump in? Ray could give some info, or maybe at the end, on how to connect with UNISEC.
Oh, how to connect UNISEC? Just email to me. Then
Yeah.
I will arrange everything. Don't worry. It's easy, very easy.
So a question somebody did ask was, what how similar and how different is the experience of developing a CanSat to a CubeSat than a traditional satellite in terms of development timelines, looking for parts, manufacturing, assembly, risk management? I guess you could look at them as, smaller and smaller they're not just smaller versions of each other, but how does a program scale differently with size?
Professor Tsuda is probably the perfect.
Yes. Yeah, difference between the ordinary satellite and the CanSat or CubeSat. Okay. Yeah, the time span is really short, and in the CubeSat or CanSat, those must be completed before the students is graduate from there. So, like in the master course, you need to fabricate everything, complete everything in like 2 years, and if students go to PhD, still this project must be 3 years or something. And actually what the way we did in the CanSat, we completed everything like a half year. And for the CubeSat, it started in 1999, and we completed everything in like 1.5 year, but waited for like 2 years for before we got the launch vehicle, so we had to wait. But yeah, like 1 or 2 years. So that's very different. So every 2 months we completed like BBM and EM engineering model and the then flight model and so on. And so everything is very fast. And for that to be possible, we always make how can I say? We try to find the way to test. So we learn from the conventional satellite development, but the like vibration test and the thermal vacuum test and so on. But we are trying to do in our own way. Like so we sometimes use it just to shake by using our hand for the vibration test, and but put the accelerometer in that and then measure the acceleration level and to meet with the requirement. And but by doing so, many people understand what we are trying to do, and then many kind of professionals lend us the environment test equipments and so on. So 2 or 3 years later, we are more good at we got more good at doing those kind of tests. But we don't we once we learn the essence of each of the process, like vibration test requires the required level of vibration, and the thermal vacuum test requires certain level of like vacuum level and also the temperature and so on. So what we have to do is to simulate that or to emulate that in our own way, based on or trying to keeping on the essence of the that testing. So in that way, we could make our own way of fabricating or developing the the satellites.
Well, let me add one thing to that. I think that that's really interesting. But the one thing that I want to point out, and I think that's part of the success of the students that work on CubeSat, is that because CubeSats are so simple and they're small, it's easier for a small group to really understand all the parts. So it's a really good systems engineering training. But the number of experts that you need, and the number of different things that you're working on is much smaller. So a small team with a few people can really understand the whole spacecraft. And I think that's one of the things that makes the training really good, is the people that come out of CubeSat don't just know power or computers or structures. They have to know everything, and they can. And then they become really good systems integrators and systems engineers. And that's very hard to do with bigger satellites. They're so complicated that it takes years to get to that level where you can see the whole spacecraft.
Thank you, Jordi. Yes, that's a really important portion. In reality, actually, in our CanSat and CubeSat, we had a team of like 15 to 20 students, and like I did in the Hayabusa 2 mission, that's a JAXA's mission. We were 600 people, but but I could be based on my experience in the CanSat and CubeSat. And that was a really good experience for me, and I could extend that experience to apply to the bigger mission.
So I'm gonna paraphrase a question here. There are a lot of universities that have put out, open source bus designs. For example, there's the Birds bus from QTech. And then there are commercial buses. I was wondering, maybe could you share your thoughts on, what is the advantages and or maybe even pitfalls of using, pre-designed spacecraft buses in your CubeSat program?
Build or buy? That's the big question. Okay, I'll start. I'll say something. I think one of the things that's very interesting is today on a CubeSat, you can buy full 3-axis attitude determination and control, 1 degree of pointing, for, I don't know, 100,000. I mean, you could never develop it on your own for that price. Even if you just give that students pizza, just the parts you have to buy and the software you have to write and all that kind of stuff. So when you get to complex CubeSat that have high performance, it's really expensive to develop everything, and it makes no sense. You have these really inexpensive things you can buy, radios and all that kind of stuff, but you learn a lot less because you're just buying that. So that's one of the reasons I think, and Bob said it, that we keep these things simple and accessible. If it's simple, you can build a whole thing. You can solder the boards, you can connect everything, and you learn a lot from that. You make mistakes, but that limits how complex and how much performance you can get out of the spacecraft. If you need that performance because your mission requires, a very accurate camera or something, it's very hard to justify. I'm going to develop everything myself, because the mass-produced components for satellite now from the CubeSat world are so inexpensive. You can do so many amazing things. I remember Klaus was showing me some of the reaction wheels that are doing in Germany, and they're just crazy. There's these tiny things, they're super well balanced, they're perfect, and they cost a reasonable amount of money. And you could never do that on your own because you don't have the capability. So I think more than a buy build thing is a decision on how complex your mission is and what you need. You probably don't want to do a very complex mission at the beginning, even if you feel you can buy everything, because it's still rocket science and it's complicated. Even if you can buy all the things, you need to make it all work together. So you may want to wait a few missions before you get into buying complex things. But when you get there, buying them makes a lot of sense. And that's just my opinion.
Yeah, I think it depends on the objective of that and the mission activity. So if you want to pursue something educational, then you have to always think about how to maximize the educational effectiveness. And that does not always mean you have to pursue very higher precision attitude control or higher data rate and so on. So you have to compromise, or you have to limit to a certain level. But you can, if you want to, if you have your students make by themselves, then they can learn much more. So yeah, I agree with Jordi.
I think here currently we have a split. We have professional high performance missions which are constructed by research teams, and we have the educational ones where simplicity and limited time frame matters. Yeah, so there are different objectives.
Oh, that's true.
Yeah, and of course they complement each other, but on the other side we see 2 avenues now branching off. And both are CubeSats, but I think it's a great benefit that we have this flexibility now in the CubeSat world, and that we have a lot of commercial components reflecting this. So we don't need to start from scratch like we had to do 20 years ago. Yeah, so we had to build a lot more. But now we can take advantage of the benefits to have such commercial items available.
again, if anyone has any questions, please ask them. We have a few about 10 minutes left. There's a question, I guess it's very pertinent and it's on everyone's mind is, do AI advances have any uh bearing on what you guys are doing for now?
The thing I can say about the AI is Chat GPT sure does write good code for processors. It's so easy to find. I used to get a lot of stuff off of YouTube and other places, but it's so easy now to just ask it Chat GPT, write me some code for this little child processor that that works with a stepper motor. Boom. May not be perfect, but it gives you what you need to tweak it a little bit and do it. It is really amazing to me that they can do that. And before we were trying to use our artificial intelligence to try and get around on the internet so we could find that code and not write it all ourselves. So I think more and more it will produce some very interesting things in the future. Now, when you put it on a spacecraft and have it do things on the spacecraft, that is something I don't know enough about it to imagine, but maybe the rest of you can see an application there.
No, I would say we never do unintelligent solutions as humans. Yeah. Sometimes we do, but usually not in technology. And so it's some kind of tautology to talk about artificial intelligence. What we surely can say is that software has an increasing role in the small satellites because miniaturization, of course, raises deficits. And the new amazing fact is that with advanced software, with filtering technology, control technologies, and so on, we can reduce the effects of disturbances. Yeah, so software in this respect plays on small satellites and using commercial off-the-shelf components helps us to reduce the effects of disturbances quite a lot and makes satellite systems more reliable when we include related redundancy concepts, also controlled by related software.
The other thing that it's going to do is going to change the software, and I think that's the key. Software processing capability is one of the big things that CubeSats were always in trouble with is the data, the amount of data we can bring down because we're power limited. So communications is very power hungry. So the data rates are slow. But if you can do a lot of the processing on board the spacecraft, then the amount of data you have to send is much less. So I think that's one of the things that's going to start happening. We won't send raw data down a lot. We'll have a lot more process results coming down from the spacecraft. And then the links get simpler and you can still do it with a CubeSat because the sensor was not the problem. The radio and the antenna, the power was the problem. And we can reduce that. It's one of those weird things where the software team can help, the radio team and the power team and everybody else by doing more work on board than on the ground.
All right, I believe we have 5 minutes. In conclusion, does anyone have any last comments they want to make?
Bob, you have to have a last comment. Otherwise, this wasn't the right kind of forum.
Well, I need to pick on Aaron here in his attempt at or not his what he's done with respect to the CubeSat history. It was one of the most educational things for me, and I hope others will have an opportunity to take advantage of what all we learned here. And I'd also like to thank the UNISEC people for putting this on, because it's always very interesting to get views from a group like yourself. So I hope that that they do this next year, because this world changes awful fast. And thank you very much.
Okay, if you're all quiet, I'll say something. Thank you as well to UNISEC for putting this together and for all they've done for years, because they've really been a pioneer in bringing CubeSats and space technology to parts of the world that nobody expected would be doing satellites, and they are now. So Ray, congrats, because you guys have done an amazing job. I always like to finish with the same thought, and that's have fun. I mean, this thing is a lot of fun. And the first time you see your satellite attached to a rocket, or you hear it beeping on the ground station, there's very few things like that. And it's a lot of fun. And if you get too bogged down into are things working and are things not working, you may forget. But don't forget to have fun and enjoy the ride, because it's really unbelievable that we can do, and so many people can do this these days, and enjoy a ride in space, which is pretty cool.
I think we still have a lot of exciting problems in front of us. And we want to thank Bob to have initiated the basis to approach them also at university level, and also for our friends at UNISEC to distribute all this knowledge worldwide. So I think it's a lot of things to be done, and let's go together.
Okay, so from me, I also would like to thank all the participants and also the UNISEC-Global meeting, UNISEC, and I would like to tell one story. This story was actually I heard this story from Professor Nakasuka about the Professor Twiggs. So one day Professor Nakasaka asked to you, Twiggs, how did you about the CANSAT? How did you come up with such an innovative idea as CANSAT? And do you remember that?
Yes, we were at a conference in Hawaii, and
right. Yes.
We had a good group of Japanese students there, and the purpose for the meeting in Hawaii is at Stanford we were building satellites and hands-on things, and at that time apparently the Japanese students weren't doing that. But one of the delightful things that I was up at the pulpit there, going on and on about building things, and I had a Coke can sitting on the thing, and I looked down at that, and we're talking about size. I looked down at that Coke can, I lifted it up, and I said, why don't we put a satellite inside of this Coke can and put it into space? And the Japanese student stood up and says, can do.
Yeah.
Is that the right story?
That's right. So yeah, I remember that clearly, and that's actually the big milestone for me, for my career. And the Professor Nakasuka actually asked when he asked about that. I think he of course expected very insightful answer from you, but your answer was because there was a Coke can.
Yeah.
So
it was a Coke can sitting on the on the
on the
podium.
table. Yeah, yeah.
And
So, but
the other
Uh-huh.
thing that Japanese have done is there's this event that they have called the Arliss Rocket
Yes.
event that's in Nevada every year, and that first thing was we put CanSats in a container that was in the top of the rocket, and they ejected that out when they got up to the apogee on it, and that becomes such an easy thing for the Japanese students. After a few years, they said, we want another challenge. We want to build a rover to put in that can, and it has to come back autonomously and to the launch site. And what they do is they launch these rockets on a big dry lake bed, and you know, that went on for 5 years. Nobody ever made it back to the flag at the launch site until the 5th year.
Yeah, yeah.
And the group that did that obviously were so excited when they saw that little rover drive up to the flag and stop. Imagine that one now. That was a real challenge because you got this carrier that is about 6 inches in diameter and about 10 inches long. You have to build a rover that fits in that, gets ejected at the apogee, comes down on a parachute, gets rid of the parachute, which some of them initially got all tangled up in the parachute, and then drive across that lake bed, which is not smooth because there's a bunch of guys get out on the lake bed when it's muddy and there's all kinds of tracks in the lake bed. And I have some movies that just absolutely are so interesting with these little rovers coming along and hitting that lake bed, and they go tumble, across it, and then all of a sudden they stop, and it's like, think of it, and then off towards the flag. Talk about ingenious designers, and I'll bet that's what they put on that asteroid project. I know one of the gentlemen that was on that said going to Nevada and doing that with the Arliss program was a really good education for him. So
True.
so many other things, the rockets, the balloons, all this other stuff, you can do an awful lot on that before you get to your CubeSat.
Yeah.
Aaron, we need to close the discussion.
Okay.
Okay. Yeah. That what I wanted to say is that everything starts from Coke can. So we have to thank that. But that's the way the innovative things happens. So innovation occurs when you walk around what you are interested in, and so staying tuned and always think about space and have fun seriously. That's a important thing.